Okay, so today we're going to be talking about fluids, and that word fluid simply means a gas or a liquid. And you might ask, you should ask, why should we bother to study fluids? Part of that, I hope, is obvious, that we are surrounded by atmosphere, so literally we are always in the presence of a fluid. So there is critically important to us the flow of air in and out of our lungs, the flow of blood in our circulatory system. Those are kind of obvious reasons why we might study it, but there are some other things that are maybe a little bit less obvious. For example, it turns out that microscopic and macroscopic animals move in very different ways when they move through water. And that difference in the way that they have to move is forced on them by the physics of fluids. Of course, air resistance is an important part of the study of fluids, and that comes into play for living flying creatures as well as for things like airplanes. Air resistance is critically important in various sports. So there's many different reasons for learning about fluids. And we'll be able to learn a lot by applying some of the physics that we have already used, that we've already learned. So let's start by talking about hydrostatic pressure. So that word hydrostatic, you might recognize, has two roots. The hydro in Greek refers to water, and the static means not changing in time. So hydrostatic pressure refers to pressure of water that is at rest, although we'll be able to use that same idea even when the water starts moving. So the hydrostatic pressure is a kind of stress. And we have had to cut stress from this class for the most part, but we need to introduce that idea just a little bit here and there in our study of fluids. So a stress is simply a force divided by an area. A hydrostatic pressure, that particular kind of stress means a force that pushes perpendicular to all surfaces, and that force comes from a surrounding fluid. So, for example, if I have a cube of metal, a solid cube of metal, and it's in the air, there is a pressure that is pushing down on the top of it from the surrounding air. That is, there's a force per unit area, and we'll do a numerical example in a moment. And there's a pressure pushing in on this side, and another one in on this side, another one in from the bottom, from the front, and from the back. So there is no net force on the cube of metal, but it's being squeezed in from all sides. So let's think about the particular example of a cardboard box in air. And let's consider a box that's sort of shaped like this, and maybe it's 6 inches this way and 12 inches this way, and it won't matter for what we're doing, but just to be definite, let's say it's 3 inches in that direction. So let's think about the force from the hydrostatic pressure of the atmosphere on this top surface of the box. The area of that top surface would be 6 inches times 12 inches, which is 72 square inches. The pressure due to the atmosphere, so 1 atmosphere of pressure, so meaning the pressure of air in the part of the atmosphere that we live in, is 14.7 pounds per square inch. And we'll talk in a little bit about SI units for pressure, but for this, let's stick with imperial units. So pressure is force over area. So we could rearrange that to get that force equals pressure times area. So that's 14.7 pounds per square inch times 72 inches squared. If you plug in the numbers on that, that's going to be around 1,000 pounds of force that is pressing downward on this top surface of the cardboard box. Now, of course, the cardboard box cannot stand up to a force of 1,000 pounds, so why is it that it doesn't crumple under this force? I'll give you a moment to think about that on your own. So why doesn't it crumple? Let's look at a side view. So here is the box. Here is that pressure pushing down on it with about 1,000 pounds of force. But the inside of the box is also filled with air, and so there is an equal force pushing upwards on it that is canceling it out. And even if you were to look inside the cardboard, so if we sort of took a look inside of it, you know that the cardboard has a kind of corrugated structure. It's made of different kinds of paper. So there's like this paper that goes up and down between the two sides. And all of this, it's all filled with air inside of it. And so let's say if we looked at this piece of paper that's folded into a zigzag going back and forth between the top and the bottom, there would be air pressure pushing in on this and pushing in on this. So all the forces are canceling out. The whole thing is saturated with air, and so all the pressure forces cancel out. But that's not always the case. So let's do a demonstration now in which we're going to be able to observe this effect in a quite dramatic way.